Good morning, everyone. Welcome to our project presentation for TRS6223 Routing and Switching project. First of all, thank you for taking time to watch our presentation. In this video, we will be presenting our project on the design, implementation, and security features of the TechNova Solution Network. Before we begin, we would like to introduce ourselves. We are from Group DCN Power. I'm the group leader. My name is Li Jieming.
My name is Li Jisheng.
My name is TVJ.
And my name is Liao Ming.
Throughout this presentation, we will explain the network design, configuration, and security mechanism that we have implemented. We will also demonstrate the result using Cisco Packet Tracer. So without further delay, let's begin our presentation. So our group consists of 4 members. Liao Ming prepare part 1 and part 2, which focus on LAN switching design, LAN trunking, and other channel. Mr. Li Jiesheng prepare part 3, which include inter-VLAN routing, HSRP, and JCP implementation. Me, Li Jieming prepare part 4, which focus on STP and network security. Mr. TJ also contribute to part 4 and participate in the packet tracer implementation and network verification process. Besides our individual section, all members work together to test and verify the overall network to ensure that all configuration function correctly. So let's welcome Mr. Li Jiesheng to start with the project scenario and objective.
This project is designed for TechNova Solutions, which consists of 2 locations, namely the headquarters and the Penang branch office. The main objective of this project is to build a scalable, reliable, and secure enterprise network that support communication between different departments and also both branches. To achieve this objective, several networking technology were implemented, including VLAN segmentations, inter-VLAN routing, DHCP, HSRP, OSPF, STP, and various security mechanisms. Besides providing connectivity, the network is also designed with redundancy and security features to ensure stable communications and improve the overall network performance.
Next, I will explain the overall network topology design for TechNova Solutions. Our network consists of 2 locations, which are the headquarters or HQ and the Penang branch. The HQ network contains 1 router, 2 layer 3 switch, 4 SS switch, and 1 DHCP server. Meanwhile, the Penang branch contains 1 router, 1 layer 3 switch, 4 SS switch, and 1 DHCP server. The 2 sites are connected through a 1 serial link between HQ router and the PG router, allowing communications between both branches. This design provides scalability, redundancy, efficient communications, and centralized network management. Moving on to part 1, which is LAN switching design and basic configuration. At HQ, 4 VLAN are implemented: VLAN 10 for IT, VLAN 20 for HR, VLAN 30 for sales, VLAN 99 for management. At the Penang branch, 4 VLAN are also implemented: VLAN 40 for engineering, VLAN 50 for finance, VLAN 60 for customer support, and VLAN 199 for management. The HQ network used 2 layer 3 switches to support inter-VLAN routing and SRP redundancy, while the Penang branch used a 3 layer 3 switch connected to a router. Next, before implementing advanced network features, basic configuration will apply in all router, layer 3 switches, and SS switch. These configurations include hostname configurations, enable secret password, local administrator account, domain name configuration, RSA key generation, SSH version 2, and password encryption. This configuration improves device security and allows secure remote management. Key configuration command. This slide shows some of the main commands used during the basic configuration process. For example, the hostname command assigns a unique device name. The enable secret path command protects privileged access. The username command creates a local administrator account. The domain name and RSA key command are required for SSH implementations. Finally, SSH version 2 is enabled to provide encrypted remote access to network devices. These configurations will apply consistently across all routers and switches in the network. Next, I'll present part 2, which focuses on VLAN, trunking, and ether channel. VLAN are used to logically separate departments into different broadcast domains. This improves network security, performance, and management. Trunking allows multiple VLAN to travel through a single physical connections between switches. Ether channels combine multiple physical links into a single logical connections to provide higher bandwidth and redundancy. For VLAN implementations, VLAN IDs and names were created for each department. Access ports were then assigned to the appropriate VLAN according to department requirements. For trunking, trunk mode was configured to allow multiple VLAN to pass between switches. For ether channel, the channel group command was used to bundle multiple interfaces into single logical port channel. This configuration ensures efficient communications and improve overall network reliability. I will now pass the presentation to my teammate who will continue with part 3, which covers inter-VLAN routing and DHCP configurations.
In the part 3, inter-VLAN routing was implemented to enable communication between different departments. Since each of the departments belong to a different VLAN, device cannot communicate directly at layer 2. Therefore, layer 3 routing is required to forward traffic between the VLANs. In this project, 2 different inter-VLAN routing methods are used. At the HQ branch, we are using layer 3 switch with switch virtual interface or SVI. This approach is suitable because the HQ branch contains multiple departments and a large number of the users. Routing is performed directly on the multi-layer switch, providing better performance and faster packet forwarding. For the pinning branch, router on a stick is implemented. A single physical interface on the router is divided into multiple sub-interfaces, and each of the sub-interface is the default gateway for a specific VLAN. In addition, OSPF dynamic routing is implemented to exchange routing information between the HQ and also the pinning branch. As a result, devices from different VLANs and different locations are able to communicate successfully. To improve the reliability, HSRP is also configured at the HQ branch. HQ Layer 3 Switch 1 acts as the active route gateway, while the HQ Layer 3 Switch 2 is served as the standby gateway. If the active device falls, the standby switch will automatically take over, ensuring the continuous network connectivity. Besides the routing, dynamic host configuration protocol is also implemented to automate IP address assignment. Without the DHCP, network administrator will need to manually configure the IP address, subname, and also the default gateway for every device, which is time-consuming and prone to human error. Therefore, several DHCP servers are deployed at both the HQ branch and also the pinning branch. Different DHCP pools are created for each department so that the device can automatically receive the correct network configuration. Since the DHCP servers are located in the management VLAN, DHCP relay agents are configured on the layer 3 device using the IP helper address command. This allows the DHCP requests from different VLANs to be forwarded to the corresponding DHCP server. As a result, users from all the departments can automatically obtain their IP address, default gateway, and also the DNS server information with simplified network administrations and also improve the scalability. Key configuration command. This slide is summarized some of the key commands used in the part 3 to enable the communication throughout the network. First, for the layer 3 was enabled on the multi-layer switch using the IP routing command. This allowed the switch at the HQ branch to perform routing between the different VLANs. Next, the switch virtual interface was created to provide default gateway for each VLAN. This interface enables the device from different departments to communicate with one another. For the pinning branch, router on a stick was implemented by creating multiple router sub-interface together with IEEE 802.1q encapsulations. A single physical interface can support traffic from multiple VLANs. In addition, HSRP was configured to provide gateway redundancy. This ensures that if the active route layer 3 switch falls, the standby switch will automatically take over and maintain the network connectivity. OSPF was also implemented as a dynamic routing protocol to exchange routing information between the HQ and also the pinning branch. This allows the device located in a different branch to communicate successfully. But finally, the DHCP relay was configured using the IP helper address command. Since the DHCP server are located in the management VLANs, the relay agent forward DHCP requests from the client VLANs to the corresponding DHCP server. The overall, this configuration provides efficiency in the VLAN communications, automatic IP address assignment, and reliable connectivity throughout the entire TISH-NOVA solution network. Now I will pass to my next team member to present.
For part 4, spanning tree protocol was implemented to prevent layer 2 loops in the HQ network. Since our access switches are connected to both HQ Layer 3 Switch 1 and HQ Layer 3 Switch 2, redundant links exist to provide backup connectivity. Although redundancy improves reliability, it can also create switching loops for custom and MAC address instability if no protection mechanism is used. Therefore, STP is used to calculate the best loop-free path and maintain a stable network environment. In our design, HQ Layer 3 Switch 1 is configured as the primary root bridge, while HQ Layer 3 Switch 2 acts as the secondary root bridge. This arrangement ensures the traffic flows in a predictable manner and provides redundancy in case the primary switch fails. Besides that, Profast and BPDU guard are enabled on user access port. Profast allows end device to start communication immediately without waiting for normal STP convergence, which help device obtain IP address faster. At the same time, BPDU guard protects the network for unauthorized switch by placing the port into an error-disabled state whenever unexpected BPDU packets are received. Overall, the implementation of STP, Profast, and BPDU guard provide a stable, efficient, and loop-free layer 2 network. This slide summarizes some of the key commands used in part 4 to provide a loop-free and secure network. First, the root bridge configuration command is used spanning tree VLAN 10 root primarily. For Profast, the example command is spanning tree Profast. BPDU guard is spanning tree BPDU guard enable. And for port security, the example command is switch port security, sticky MAC address, switch port security MAC address sticky, and for disable unused port, we are using shutdown to disable the port. Besides maintaining a loop-free network, we also implement several security mechanisms to strengthen the access layer. The main objective of endpoint security is to ensure that only only authorized devices are allowed to access the network. Since access ports are the closest point to end user, they are also the most common target for unauthorized access and layer 2 attack. Several threats may exist in a switch network, including unauthorized device connection, MAC floating, robo switch, VLAN hopping, robo DHCP server, and ARP spoofing attack. To reduce this risk, port security was implemented on all user-facing interface. Sticky MAC address learning allows the switch to automatically learn legitimate MAC address while violation mode is configured as shutdown. Therefore, if an authorized device is connected, the switch will automatically disable the port to prevent access. In addition, unused ports are administratively shut down to prevent attackers from connecting unknown devices to the network. DHCP snooping and dynamic ARP inspection are also implemented to provide protection against robo DHCP server and ARP spoofing attack. Overall, this security mechanism improves the confidentiality, integrity, and availability of Teknova solution network and provide a more secure and reliable network infrastructure. Now, let's move on to the practical of our presentation. Mr. TUJ will demonstrate the actual configuration and testing result in Cisco Packet Tracer to verify that all components of the network are functioning as intended.
So now I'm going to do the packet tracer demonstration. So firstly, I will demonstrate the VLAN implementation in our network. And HQ, we create a VLAN 10 for the IT, VLAN 20 for the HR, VLAN 30 for the sales, VLAN 99 for the management. With the Penang branch, the VLAN 40 is engineering, VLAN 50 is finance, VLAN 60 is customer support, and the VLAN 199 is management. So for the HQ part, show the VLAN brief. So for the output, we can verify that the VLAN has been successful create and the switch point and assigned to the correct VLAN. So for the part 2.1 trunking, to allow multiple VLAN to pass through a single link between the switch, trunking is configured using 1EEE X02.1Q. So interface trunk. So the output shows that the trunk ports are active and carrying the required VLAN. This allows communication between the VLAN and network device through the uplink connection. So for the part 2.2, enter channel. Enter channel is implemented in the Penang branch. Enter channel combines multiple physical links into the one logical link. The advantages are increase the bandwidth and redundancy. If one cable fails, communications still can continue use the remaining link. So the port channel are shown as SU. S indicate layer 2 enter channel, and U indicate that the enter channel is operated and currently in use. So for the part 3.1, inter VLAN routing in the HQ branch. At the HQ, inter VLAN routing is implemented using a layer 3 switch. Switch virtual interface SVI are configured for each VLAN. So this VLAN interface are act as the default gateway for their own department. So the routing table shows that all VLAN networks are directly connected to the layer 3 switch. Therefore, devices from different VLAN can communicate with each other. So for the part 3.1 router on the stick, for the Penang branch. So at the Penang branch, inter VLAN routing is implemented using the router on the stick. A single physical interface are delivered into the multiple logical sub-interface. So each sub-interface represents one VLAN and server as a gateway for the VLAN. So part 3.2, DHCP. DHCP is implemented using the DHCP server. This allows host to obtain IP address automatically without manual configure. So now I will add one new PC for the IT department, and I connect it. After that, I'm trying to request the DHCP. So when I get IP, meaning that DHCP is successful. So after that, so first I will test the communication between the hosts within the same VLAN. So it's successful. For the testing 2 different VLAN. So the successful reply confirm that inter VLAN routing is functional correctly. So for the testing 3, HQ to Penang. the successful response proved that the routing between the HQ and the ping is worked correctly. So for the part 4.1, STP. So to prevent the switching loop, spanning tree protocol is implemented. So at the HQ layer 3 switch 1, HQ layer 3 switch 1 is configured as a root bridge, and the HQ layer 3 switch 2 is configured as the root secondary bridge and act as the backup root bridge. So for the other implementation, so we open the HQ switch 2 to show the another security config. So the switch port security in layer 2 switch port security is enabled to prevent an unauthorized device from connecting to the network. The switch port security maximum 2. The maximum number of MAC address allowed on this port is limited to 2. If more than 2 devices attempt to connect through the hub and unauthorized switch, the port security machine will detect the volunteers. So for the switch port security MAC address sticky MAC address is learning enabled. The switch automatically learn and store the MAC address for the device and connected to this port. So for the switch port security MAC address sticky 0002.1755.4 BBD. The MAC address has been learned and secured as a trusted device. Any unknown MAC address attempting to use this port will be considered unauthorized. This helps prevent the MAC spoofing attack and unauthorized endpoint connection. It improves the layer 2 security by ensuring only approved device can access the network. Spanning tree port fast. Port fast is enabled on access port connected to the end device. It allows the port to immediately after following stage without waiting for a normal STP process. This reduces the startup delay experienced by the user when connected to the network. Spanning tree BPDU guide enabled. So BPDU guide is enabled to protect the network from unauthorized switch. If an BPDU package is received on this access port, the port will automatically shut down. This prevents the accident loops and protect the stability of spanning tree topology. And for the discretion unsafe port, we disable the unsafe port and we put it as name is unused port. We also shut down the port. So in conclusion, the network has been successfully implemented according to the project requirement. VLAN stagnation improve the network organization. Trunking and inter-channel provide efficient communication and redundancy. Inter-VLAN routing enable the communication between the department. DCP automatically assign IP address. STP prevent the switching loop. Security features such as port security, port fast, and BPDU guide help to protect the network from attack. All connectivity tests between the VLAN and between HQ to the ping branch was successful. So that's all for our group. Thank you.
Thank you.
Thank you.
Thank you.